Every few months, the same video goes viral. A giant robotic arm effortlessly squeezes gray concrete out of a nozzle, back and forth, printing an entire house in 24 hours. Three-dimensional concrete printing has moved out of the laboratory. It is a working construction method right now. Hundreds of homes have been built with it in the United States. Australia is using it for social housing, and Dubai has actively written it into government policy. But the printed in 24 hours headline skips over the physical reality of the job site. The viral clips are hiding the messy, complicated constraints of the material itself. To figure out if this technology actually solves the housing crisis, we have to look past the push-button internet fantasy and see how it works in the mud. Conventional concrete construction relies on formwork, temporary timber or steel molds built to hold wet concrete in place until it hardens. Building, bracing, stripping, and throwing away those molds accounts for a massive share of the labor and waste on any job. 3D printing removes that step entirely. The material has to hold its own shape the exact second it leaves the nozzle. To achieve this, the machine cannot use the standard concrete that arrives in a ready-mix truck. It requires a highly engineered, chemical-heavy mortar. Engineers are forcing this mortar to do two contradictory things at once. It must flow easily through pumping hoses as a soft liquid, but turn into a rigid solid instantly to carry the next layer's weight. If too stiff, it clogs the line. If too soft, the wall buckles under its own weight. Even when the printer navigates that tightrope perfectly, it only produces the wall system. The foundation is poured conventionally before printing starts. The roof is framed by traditional trades, who also come in later to install windows, plumbing, wiring, insulation, and cabinetry. The printed wall system represents roughly 15 to 30% of the total construction cost, leaving the vast majority of the budget and labor to traditional building methods. Printing that shell does offer undeniable schedule advantages. In a recent Australian social housing project, substituting traditional framing for a printed wall system cut the expected structural timeline roughly in half. It also creates total geometric freedom. In traditional construction, curved walls require custom molds and expensive labor. Because a robot simply follows a digital file, a complex curved structure like this one costs exactly the same to print as a straight line. But concrete is strong in compression and weak in tension. To survive heavy loads, high winds, or seismic activity, it requires steel reinforcement. Traditional builders solve this by pouring wet concrete over a cage of tall steel rebar. Layer-by-layer printing leaves no structural space for vertical steel, restricting most of these buildings to low-rise designs. Furthermore, if a bottom layer dries out before the nozzle adds the next layer, the two materials fail to bond. Engineers call this a cold joint. These weak seams create direct pathways for water. Experimental testing on printed walls show they are highly vulnerable to wind-driven rain leaking straight through the concrete and into the living space. Deleting formwork buys rapid speed and architectural flexibility. We trade those benefits for a structure that struggles with basic tensile strength and water resistance. We also need to evaluate the environmental claims. The machine places material only where it is required, which drastically reduces job site waste. But the specialized mortar required to make the whole system work hides a high environmental cost. To achieve rapid stiffening, printable mixes require a significantly higher cement content than standard cast concrete. Because cement production is the primary driver of concrete's emissions, a printed wall can actually carry a higher embodied carbon footprint than a conventionally built one. Then there is the reality of the labor market. Accelerating the assembly of the walls does nothing to resolve the severe industry shortages of electricians, plumbers, and roofers. A rapidly printed shell will sit idle in the dirt waiting for municipal utility hookups, specialized finishes, and permitting, exactly like these traditional timber-framed builds. The most credible application for this technology is hybrid construction. It excels at remote emergency shelters, custom foundations, and printing modular components that feed into conventional builds, rather than printing entire sprawling suburbs. 3D concrete printing improves how we execute specific structural phases. Its value lies in compressing schedules for particular projects, though the systemic issues of land cost, zoning, and trade shortages continue to dictate the pace of housing delivery. Knowing what actually goes into the walls, would you live in a printed house? Let us know down in the comments.